Welcome! In this session, we'll explore an exciting problem titled Count Good Meals from LeetCode. The challenge involves identifying pairs of indices whose values sum up to a power of 2. Let's dive in and break it down step by step. In this problem, we are tasked with counting the number of good meal pairs in an array. A good meal is defined as a pair of integers from the array, such that their sum equals a power of 2. Powers of 2 include numbers like 1, 2, 4, 8, 16, and so on. For example, if two numbers add up to 4, which is 2 to the power of 2, that would constitute a good meal. The input is an array called deliciousness, where each element represents the deliciousness value of a meal. We need to find all such good meal pairs in the array. Since the size of the array can be very large, up to 100,000 elements, and the values themselves can go up to 2 raised to 20, the solution must be efficient. Finally, because the number of such pairs could also grow very large, the result must be returned modulo 10 to the power of 9 plus 7 to keep it manageable. Now, let's look at an example to understand this better. Suppose the input array is deliciousness equals 1, 3, 5, 7, 9. The output in this case is 4, meaning there are 4 good meal pairs. These pairs are 1, 3, because 1 plus 3 equals 4, which is 2 to the power of 2, 1, 7, because 1 plus 7 equals 8, which is 2 to the power of 3, 3, 5, because 3 plus 5 equals 8, which is also 2 to the power of 3, and finally, 7, 9, because 7 plus 9 equals 16, which is 2 to the power of 4. This example highlights how we need to check all pairs in the array to find sums that correspond to powers of 2. Here's another example where the input array is deliciousness equals 1, 1, 1, 3, 3, 3, 7. The output for this input is 15, which includes many good meal pairs due to the repeated values in the array. For instance, there are 3 pairs of 1, 1, since 1 plus 1 equals 2, which is 2 to the power of 1. Similarly, there are 3 pairs of 1, 3, because 1 plus 3 equals 4, which is 2 to the power of 2. There are also 3 pairs of 3, 7, as 3 plus 7 equals 10, which is 2 to the power of 3. The presence of duplicate values in the array greatly increases the number of valid pairs, so the solution needs to account for this efficiently without explicitly checking every possible pair. To solve this problem effectively, we need to consider several constraints and edge cases. First, if the array contains only one element, no pairs can be formed, so the result is 0. Similarly, if all elements are 0, any pairs formed will sum to 0, which is not a power of 2, so the result is also 0. In cases where all elements are the same, like deliciousness equals 1, 1, 1, we must carefully count combinations of pairs to avoid overcounting. Finally, for large arrays with many duplicate values, an efficient algorithm is essential. A naive approach with O(n)² complexity, which checks all pairs, would be too slow. Instead, we need an optimized solution that leverages properties of powers of 2 and avoids unnecessary computations. To solve the problem of counting good meals, we need to identify pairs of indices where the sum of their deliciousness values equals a power of 2, such as 1, 2, 4, 8, and so on. One straightforward approach to address this is the brute force method. Here, we iterate through every possible pair of indices, calculate their sum, and check if it equals a power of 2. For this check, we can either repeatedly divide the sum by 2 or use a pre-computed set of valid powers of 2. If the condition is satisfied, we increment the count of valid pairs. While this method is simple and intuitive, it has a time complexity of O(n)², because we examine every possible pair, and it uses O(1) space since we only need counters and temporary variables to keep track of results. However, as we'll see, this approach is not efficient enough for larger input sizes. The brute force approach, while simple, has significant drawbacks. Its O(n)² time complexity makes it impractical for larger arrays, especially when the input size approaches the upper limit of 100,000 elements. To address this inefficiency, we turn to an optimized approach that leverages a hash map. The key insight here is that instead of rechecking sums for every pair, we can store and reuse information about the frequencies of previously encountered elements. As we iterate through the array, for each number, we calculate its potential complements, values that, when added to the current number, form a power of 2. Using a hash map, we can efficiently check how many of these complements have been encountered so far. This optimization hinges on the observation that a sum equals a power of 2 if and only if it matches 2 raised to some integer power. By counting valid complements dynamically, we avoid redundant computations and significantly improve efficiency. To implement this optimized approach, we start by pre-computing all powers of 2 that are relevant for the problem. Since the maximum possible sum of 2 elements in the array is 20,000, we only need powers of 2 up to 2 to the power of 21. Next, we initialize a hash map to store the frequencies of elements as we process the array. As we iterate through the array, for each number, we calculate its complements by subtracting it from each pre-computed power of 2. If any of these complements exist in the hash map, we retrieve their frequencies and add them to our count of good meals. After processing the complements, we update the hash map by adding the current number to it. This approach has a time complexity of O, n asterisk m, where n is the array length and m is the number of powers of 2, which is approximately 22. This is a significant improvement compared to the O, n squared, complexity of the brute force approach. Moreover, the space complexity is O, n, which is manageable within the problem's constraints. This method is both efficient and scalable for larger input sizes. While the optimized hash map approach is more complex than the brute force method, its efficiency makes it the preferred strategy for this problem. By pre-computing powers of 2 and dynamically checking for complements using a hash map, we achieve near-linear performance for practical input sizes. The trade-off is a slight increase in space usage, which is acceptable given the constraints. Other alternatives, such as sorting the array and using a two-pointer technique, introduce additional complexity, like handling duplicates, and require an O, n log n, sorting step. Dynamic programming is also possible but unnecessary since the hash map approach already achieves optimal performance. Ultimately, the hash map strategy strikes the best balance between clarity and efficiency, making it the ideal choice for solving the problem of counting good meals. To solve the problem of counting good meals, we first need to define what constitutes a good meal. A good meal is a pair of indices, I, j, where the sum of their deliciousness values equals a power of 2, such as 1, 2, 4, 8, and so on. Additionally, the condition I less than j must hold to ensure unique pairs. Now, before diving into the algorithm, we start by understanding the range of powers of 2 that are relevant. Since the maximum sum of 2 values is twice the largest value in the array, we compute all powers of 2 up to this limit. For instance, if the maximum value is max_val, the largest power of 2 we consider is 2 to the power of k such that 2 to the power of k is less than or equal to 2 asterisk max_val. This pre-computation step ensures that we know exactly what sums to check for when iterating through the array. Next, we prepare to use a hash map to store frequencies of deliciousness values. This data structure is chosen because it allows for fast lookups, making it ideal for checking how many times a complementary value has appeared as we iterate through the array. With these two foundational steps in place, we're ready to process the array efficiently. Now, we move on to the iterative part of the algorithm. For each deliciousness value x in the array, we systematically check it against all pre-computed powers of 2. For each power of 2, denoted as p, we calculate the complement c, which is simply px. The goal is to determine if this complement has been seen previously in the array. If the complement exists in the hash map, its frequency tells us how many pairs can be formed with the current value x. We then add this frequency to our total count of good meals. Once the checks for x are complete, we update the hash map by incrementing the frequency of x to include it for future iterations. This ensures that each value is considered as a potential complement for subsequent elements. To handle the possibility of very large counts, we take the result modulo 10 to the power of 9 plus 7 during each addition. This prevents overflow and ensures the result stays within the constraints of the problem. Finally, after iterating through the entire array, the total count represents the number of valid pairs, which we return modulo 10 to the power of 9 plus 7. To make this process clearer, let's walk through a detailed example. Suppose the input array is 1, 3, 5, 7, 9, and the relevant powers of 2 are 1, 2, 4, 8, 16, 32. We start with an empty hash map to store frequencies. For the first value, x equals 1, we calculate its complements with each power of 2, 1, 0, 2, 1, 4, 3, 8, 7, and so on. Since the hash map is empty, none of these complements exist yet. We then add 1 to the hash map with a frequency of 1. Next, for x equals 3, we again calculate complements for each power of 2. When we reach the complement 1, it is found in the hash map with a frequency of 1, so we add 1 to our count. The hash map is then updated to include 3 with a frequency of 1. This process continues for all other values in the array, with each step checking for complements, updating the count, and adding the current value to the hash map. At the end of the iteration, the total count reflects the number of valid pairs that form good meals. The key insights of this algorithm lie in its efficiency and careful handling of constraints. By pre-computing powers of 2, we eliminate redundant calculations during the iteration. Using a hash map to store frequencies allows for constant time lookups, making the process of checking complements fast and efficient. To avoid double counting pairs, we ensure that each value is added to the hash map only after all its complements have been checked. The modulo operation, applied at every step, ensures that the result remains within the constraints of the problem and prevents integer overflow. In terms of complexity, the algorithm runs in O, n*k, where n is the size of the array and k is the number of pre-computed powers of 2. The space complexity is O, n, as we store the frequency of each value in the hash map. Together, the use of pre-computed arrays and a hash map ensures that the solution is both time and space efficient, making it well suited for large inputs. This combination of techniques highlights the elegance and practicality of the algorithm in solving the problem efficiently. This Python implementation solves LeetCode problem number 1711, count good meals, by efficiently counting the number of good meal pairs. A good meal is defined as a pair of numbers whose sum equals a power of 2. The code begins by importing the counter class from the collections module, which is essential to count occurrences of numbers efficiently. The countPairs method is implemented within the solution class, and it takes a list of integers, deliciousness, as input. Key steps. 1. Pre-compute powers of 2. The variable powers _of _2 stores all relevant powers of 2, from 2 to the power of 0 to 2 to the power of 21. These values represent the possible sums we need to check. 2. Hash map for counting frequencies. The count variable, a counter, is used to store the frequency of each number seen so far in the list. 3. Iterate through the list. For each number in deliciousness, the code iterates over the pre-computed powers _of _2 to calculate the complement, the number needed to form a sum equal to the current power of 2. 4. Count valid pairs. If the complement exists in the count hash map, it means there are valid pairs formed with the current number. The count of such pairs is added to the pairs variable. 5. Update the frequency map. After checking for pairs, the current number is added to the count hash map to ensure it is considered for future complements. 6. Modulo operation. Since the result can be very large, the final pairs count is returned modulo 10 to the power of 9 plus 7. Complexity analysis. The algorithm efficiently handles the problem with a time complexity of O, n*k, where n is the length of deliciousness and k is the number of powers of 2, 22 in this case. The space complexity is O, n, due to the hash map used to store frequencies. This approach ensures performance remains optimal even for large inputs, adhering to the constraints of the problem. This is the Java implementation of LeetCode problem number 1711, count good meals. The code mirrors the Python logic, using a hash map to store counts of numbers and iterating over powers of 2 up to 2 to the power of 21. Key differences include explicit type declarations in Java, the use of a hash map instead of Python's counter, and bit shifting for calculating powers of 2. The solution efficiently computes the number of valid pairs with a time complexity of O, n*log, max power. To solve the problem, we start by initializing a few key variables. First, we define mod as 10 to the power of 9 plus 7 to handle large numbers during calculations. Then, we pre-compute all powers of 2 up to 2 to the power of 21, storing them in the array powers _of _2. This gives us values like 1, 2, 4, 209, 7152. Next, we initialize a counter object called count to keep track of how many times each number has appeared, and we set pairs to 0 to count the valid pairs we find. Let's process the first number in the input array, 1. For each power of 2, we calculate the complement by subtracting the current number, 1, from the power. Since count is initially empty, no complements match. We then add 1 to the count, making it 1, 1. Moving on to the next number, 3, we repeat the process. For the power of 2 equal to 4, the complement is 4 minus 3 is equal to 1. Since 1 exists in count, we add its frequency, which is 1, to pairs. This gives us one valid pair so far. We then update count to include 3, resulting in 1, 1, 3, 1. Next, we process the number 5. For the power of 2 equal to 8, the complement is 8 minus 5 is equal to 3. Since 3 is in count, we add its frequency, which is 1, to pairs, bringing the total count of pairs to 2. The count is then updated to include 5, giving us 1, 1, 3, 1, 5, 1. Moving to the number 7, we find that for the power of 2 equal to 8, the complement is 8 minus 7 is equal to 1. Since 1 exists in count, we add its frequency, which is 1, to pairs. This increases the total pairs to 3. We then update count to include 7, resulting in 1, 1, 3, 1, 5, 1, 7, 1. Finally, we process the number 9. For the power of 2 equal to 16, the complement is 16 minus 9 is equal to 7. Since 7 is in count, we add its frequency, 1, to pairs, which now becomes 4. We update count to include 9, resulting in 1, 1, 3, 1, 5, 1, 7, 1, 9, 1. After processing all numbers, the total number of pairs is 4. Applying the modulo operation, pairs % mod equals 4, gives the final output. In this example, the input array is 1, 1, 1, 1. The initialization is the same as before, with mod, powers underscore of underscore 2, count, and pairs set up. When we process the first occurrence of 1, no complements match because count is empty. We then update count to 1, 1. For the second occurrence of 1, we calculate the complement for the power of 2 equal to 2. The complement is 2 minus 1 is equal to 1, and since 1 exists in count, we add its frequency, which is 1, to pairs. This makes the total pairs 1. We update count to 1, 2. For the third occurrence of 1, we again find the complement 2 minus 1 is equal to 1. Adding its frequency, which is now 2, to pairs brings the total pairs to 3. The count is updated to 1, 3. Finally, for the fourth occurrence of 1, the complement 2 minus 1 is equal to 1 results in adding its frequency, 3, to pairs. This makes the total pairs 6. Updating count gives 1, 4. After processing all numbers in this example, the total number of pairs is 6. Applying the modulo operation, pairs % mod equals 6, gives the final output. Now, let's consider another example where all the numbers in the input array are identical but larger. The input array is 32, 32, 32, 32. Initialization is the same as before. For the first occurrence of 32, no complements match because count is empty. We update count to 32, 1. For the second occurrence of 32, we calculate the complement for the power of 2 equal to 64. The complement is 64 minus 32 is equal to 32, and since 32 exists in count, we add its frequency, which is 1, to pairs. This gives us one pair so far. We update count to 32, 2. For the third occurrence of 32, the complement 64 minus 32 is equal to 32 again matches. Adding its frequency, 2, to pairs brings the total pairs to 3. The count is updated to 32, 3. Finally, for the fourth occurrence of 32, the complement 64 minus 32 is equal to 32 matches once more. Adding its frequency, which is 3, to pairs increases the total pairs to 6. Updating count gives 32, 4. After processing all numbers, the total number of pairs is 6. Applying the modulo operation, pairs % mod equals 6, gives the final output. This concludes the walkthrough of the solution, demonstrating how we systematically calculate valid pairs for a variety of inputs by leveraging the properties of powers of 2 and an efficient counting strategy. To understand the time complexity of our solution, we start by breaking it into its components. First, we have the outer loop that iterates over each element in the deliciousness array. If the length of the array is n, the outer loop runs exactly n times. Next, within the outer loop, there is an inner loop that iterates over a list called powers underscore of underscore 2. This list contains 22 elements, representing powers of 2 from 2 to the power of 0 to 2 to the power of 21. Since the size of this list is fixed, the inner loop runs 22 iterations for each element in deliciousness, which is a constant number of iterations. Additionally, within the inner loop, we perform a dictionary lookup to check if a complement exists in the count dictionary. This lookup operation has an average case time complexity of 1, thanks to Python's efficient dictionary implementation. Lastly, updating the count dictionary is also an 1 operation. So, each step within the inner loop is constant time. Now we combine all these components to calculate the total time complexity. The outer loop runs n times, and the inner loop runs a fixed 22 iterations, which simplifies to 1. Since the operations inside the inner loop, such as dictionary lookups and updates, are also constant time, the total time complexity becomes n multiplied by 1, which simplifies to n. Moving on to space complexity, we consider the additional memory used by the solution. The first contributor is the powers underscore of underscore 2 list, which contains 22 integers. As the size of this list is constant, it adds 1 to the space complexity. The primary contributor to space complexity in this solution is the count dictionary. This dictionary is used to store the frequency of elements in the deliciousness array. In the worst-case scenario, where all elements in the array are unique, the dictionary will store n entries. Each entry consists of a key-value pair, with the key being the element and the value being its frequency. The total space required for n entries is n. Therefore, the overall space complexity is n for the count dictionary, combined with the 1 from the powers underscore of underscore 2 list. Altogether, the total space complexity of our solution is n. Let's compare this optimized approach to a brute force method. In a naive approach, we would generate all possible pairs of elements in deliciousness and check if their sum is a power of 2. Generating all pairs involves iterating through the array twice, resulting in n squared time complexity. Checking if a sum is a power of 2 is an 1 operation, so the total time complexity for the brute force method is n squared. The space complexity is 1, as no additional data structures are used. In contrast, the optimized approach leverages a hash map to store frequencies and avoid redundant computations. This reduces the time complexity to n, though it introduces an n space requirement for the dictionary. Overall, the optimized approach is significantly faster for large inputs, making it a better choice for this problem. Finally, let's analyze the best, average, and worst-case scenarios. In the best case, all elements in deliciousness are the same. Here, the count dictionary will contain only one entry. However, we still need to iterate over all elements, so the time complexity remains n. In the average case, the dictionary size grows proportionally to the number of unique elements in the array, and the time complexity remains n. The worst case occurs when all elements in deliciousness are unique, resulting in a dictionary size of n. Even in this scenario, the time complexity stays n. Mathematically, the inner loop runs a fixed 22 iterations for each of the n elements, and with 1 operations inside, the total time complexity simplifies to 22 n, which is n. Space complexity is proportional to the number of unique elements, leading to a maximum of n. When working on this problem, there are some common mistakes to watch out for. First, iterating over an unbounded range of powers of 2 can lead to unnecessary computations. For example, if you check powers of 2 far beyond 2 to the power of 21, you're wasting time because the constraints limit the deliciousness values to a maximum of 2 to the power of 20. Instead, focus on powers of 2 up to 2 to the power of 21, as the largest possible sum is 2 to the power of 20 plus 2 to the power of 20. Another frequent mistake is using a nested loop to check every pair of deliciousness values. This results in an n squared complexity, which becomes impractical for larger arrays. A better approach is to use a hash map to keep track of previously seen values, enabling you to solve the problem in n*m, where m is the number of relevant powers of 2. Lastly, be cautious about handling duplicate pairs. Counting both I, j, and j, I as separate pairs can lead to overcounting. Make sure you only count each valid pair once, either by focusing on combinations rather than permutations or by ensuring that each value is processed appropriately. Another mistake to avoid is overlooking modular arithmetic when dealing with large outputs. In many problems, including this one, results might exceed standard integer limits, so you need to apply a modulo operation at every step of the calculation, typically using mod 10 to the power of 9 plus 7. This ensures that your results stay within bounds and prevents overflow. Next, zero values require special attention. 0 isn't a power of 2, but it can form valid pairs under specific conditions, such as when the sum equals a small power of 2. To handle this correctly, you need to account for 0 separately, ensuring it contributes only to valid pairs. Ignoring this nuance can lead to missed solutions or incorrect results. This problem is a great opportunity to showcase your ability to optimize solutions by spotting patterns in the constraints. For example, recognizing that the deliciousness values are limited and that the target sums are restricted to powers of 2 helps you avoid brute force computations. A hash map is a key tool here, as it allows you to efficiently store frequencies of elements and check for their complements. Make sure you can explain how this approach reduces the complexity and why it's more efficient than alternatives. Also, don't forget to address important edge cases, such as empty arrays, arrays with only one element, or arrays with repeated values. Communication is critical during an interview, so walk your interviewer through your thought process step by step. For instance, explain why you chose a specific range of powers of 2 and how you avoided counting duplicate pairs. Additionally, this problem connects to several others, like toSum, for sum 2, and subarray sum equals k, which all involve hash map-based strategies. Studying these related problems can deepen your understanding of the underlying techniques. There are several approaches you can take to solve this problem, each with its own trade-offs. A brute force approach involves iterating through all pairs of indices and checking if their sum is a power of 2. While simple to implement, this method has a time complexity of n squared, making it infeasible for larger inputs. A more efficient solution uses hash maps to optimize the process. By tracking the frequencies of numbers and checking for their complements among the powers of 2, you can achieve a complexity of n*m, where m is the number of relevant powers of 2. This approach is scalable but requires careful handling of duplicates and modular arithmetic. Another alternative is to use bit manipulation to exploit the binary properties of powers of 2, such as the fact that only one bit is set in their binary representation. While this method can also achieve n*m complexity, it may be harder to implement and debug compared to the hash map strategy. Ultimately, the choice of approach depends on the constraints and the specific requirements of the problem. Thank you for joining me in solving the Count Good Meals problem. Today, we learned how to optimize pairwise calculations using hash maps and identified key concepts like pre-computing powers of 2. Remember, practice makes perfect, keep tackling problems, and you'll see your skills grow. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!